So today we have Leo Milecki, who comes from CentraleSupelec, the mixed laboratory, which is kind of big computer science lab, right?
Yes.
Including many people. So he works with Maria Volopoulou, which I know very well, in fact. So it's an excellent medical image analysis group there. And so Leo is at the end of his PhD, I believe, last year, I guess. And he will be talking about interesting subjects, including contrastive pre-training, I think, and like subjects that should be of interest to us, and along with some interesting also clinical problem behind. So yeah, and he was visiting in Montreal for 3 months on internship in Provost Lab. It's an ultrasound lab at the University of Montreal, because also he works on ultrasound, both MRI and ultrasound. So floor is yours, and thanks for coming.
Thank you. So yes, I will try to give a talk on my latest work during my PhD, which is data-driven methods for renal transplant monitoring. So the goal is to do some cool deep learning methodologies, but for a specific application, which is to monitor renal transplant, so the kidney. Okay. Okay. So just.
Are you sharing the screen?
Yes, I'm sharing, but it's just that it will be difficult if I have to change the slide. Yeah. But okay, it's fine.
I make it just closer to you.
Yes, thanks. So the outline of this presentation is the following. Like first, I will introduce the medical context of my project. Then I will present you my latest work on prognosis from DC MRI data, which is titled Contrastive Mass Transformers for Forecasting Renal Transplant Function. And then I will briefly introduce you my current future work, so that if you want to discuss later, it will be interesting. And yes, so starting with the medical context. Renal transplantation is considered as the most effective solution for end-stage renal disease patients. And the problem is that transplants may lead to allograft rejection or dysfunction in the first 5 years, for example, within 15 to 27% of the patients. And the phenomena at stake when having a resection are quite diverse and complex in the organ itself. So in clinical practice, resulting from a blood test, creatinine, which is in your blood, is the primary diagnostic tool to indicate the overall function of the graft post-transplantation. But this method is less sensitive and considered a late biomarker for the dysfunction of the graft. So if those blood results are irregular, the gold standard method is needle biopsy. So it's a surgical operation, which is not favorable, of course, because it's invasive, time-consuming, expensive, and it can cause injurious events to the patients. So a non-invasive alternative using medical imaging, which has the ability to provide some early and accurate diagnosis, is crucial to fulfill this clinical need. So I will present you my latest work, which has been published at Milecki on contrastive mass transformers for forecasting renal transplant function. So which is joint work with 2 hospitals in Paris, so with medical doctors, and with the LIX lab at École Polytechnique in France. So starting for the challenges for this task. So first, to learn with few data samples, so few patients in this specific setting for medical imaging. So in the field of renal transplantation, diagnosis or prognosis using medical imaging. Recent studies focused on detecting specific events or assessing the overall graft function status at the time of the exam, like in a more like supervised way. You can see it using one exam and the actual status, and trying to predict from the images what is diagnosis. Also, we have to deal with missing data, as we will see later. So data imputation methods originally proposed to fill the missing data upstream, like a pre-processing step to the data, with the simply thing would be to take the mean of the data or searching statistical. But like when having like medical imaging data, it's something that you don't want to do, of course. And there are some generative models which have showed promising results to impute the missing data, but they require a big amount of data to train to have good results. And the last point is to incorporate longitudinal information, because we have several exams after the transplant. So as you all know, I guess transformers demonstrated their success for sequential data, while the attention mechanism showed promising results only missing data for structural data. So yeah, structural data and, for example, trajectory data. So concerning those three main challenges, here are our contributions. So first, to propose medical specific retrainings based on contrastive learning to learn good representations of our MRI data. Then to tailor the method to handle the missing follow-up exams, and to use transformers for renal transplant function prediction from the sequential data. So now I will continue with the dataset. So we have 89 patients, which are all subject to kidney transplantation, having DC MRI. So DC is a dynamic contrast enhanced. So you inject a contrast agent into the patient, and you take several acquisitions where you see the contrast agent flowing into the patient at 4 follow-up exams, which are at 15 days, 30 days, 3 months, and 1 year after the transplantation. And we use like a trained set of 69 patients and a test set of 30, which is one of the main bottleneck of our method. So the problem of missing data, all the patients didn't go to all the follow-ups, so we have those numbers of available exams respectively to the different exams. And each exam include 5 to 9 acquisitions while the contrast agent is flowing to the patients. So here you have an example. You have 3 slices of 4 different acquisitions for the same patient, same exam. So you can see, for example, I think the time order is like this, A, B, C, D. You can see the contrast agent flowing into the organ. So for our pre-trainings, we interested ourselves to incorporate clinical prior to the training of the representation of the MRIs using clinical variables, which were suggested by nephrology experts as important, having a important coefficient regarding the graft survival, which are the transplant incompatibility, which is a variable which resumes that the organ was compatible with the patient with the receiver of the organ, the donor's age, which is simply the age of the donor of the kidney, and the GFR, which is computed using the serum creatinine value, so which is a biomarker of the the actual status somehow of the organ. So to pre-train our model, we have like a quite big data set overall, because only having 89 patients using the up to 4 follow-ups and all the different acquisition of DC MRI, we have about 1,500 volumes. So this is an overview of our proposed method, which is we want to predict the kidney function 2 years post-transplantation. At the bottom, you have like a timeline where D0 is the transplantation date. You have the 4 imaging exams, and you have the prediction 1 year after the last exam, so 2 years post-transplantation. So first, as I said, we build a big data set of all our MRI data to pre-train a feature extractor encoder, so which is simply a ResNet 18 model using contrastive learning. And then we use one specific time acquisition, which is called by doctors the tubular time, which is where the whole kidney is enhanced. And we generate for each follow-up the features, which we input to a sequential architecture using the transformer architecture to predict this kidney function classification task, where we use the mean value around 2 years of the serum creatinine, where the threshold used here is saying, is this a non-normal or normal value? And as you will see, we include a mask to handle missing data if we have missing exams for, we do have missing data for many patients. So first, the contrastive learning part. We use a two-stream scheme where we consider pairs of volumes, and we encode the volumes to a feature space using a ResNet 18 and embedding head. And what we do is we train our model based on this loss function, which is based on the cosine similarity between the two features, which is in 2D the angle, well, in 2D it can be easily seen as the angle between the two features. And what we say is that if the label associated to the pair is 1, we want the features to be near, so the angle to be low. And if the features, if the label is 0, we want the features to be far. So here we have an example. If the label is 1, we want them to be in this area, and if the label is 0, we want them to be this area. So now the question is, how do we set this label L? So we propose 2 ways. The first one is quite simple and can be seen as self-supervised, because we use only the information which is what patient comes from this volume. And we say label is equal to 1 if the 2 MRIs, the 2 volumes come from the same patient. So if it comes from the same patient, we want the features to be near, and the opposite if not. The second option that we propose is weakly supervised. It's where we use the variable I've introduced before. And we say that if this clinical variable is not near, but if the difference is in the 2 variables is quite low, we want the features to be near in the feature space. So we just compute using a threshold the absolute difference between the 2 variables for those 2 volumes. And if not, we label the pair 0. And so theta is set accordingly to the different variable we use, using the insights from the doctors. So Two relevant training details, which I think made this whole training work, is using first curriculum learning. So the idea overall of curriculum learning is to increase the adversity of the task you're trying to solve during the training. So, for example, for the first option, we include pairs from the same exam and the same patient in the first half of the training, and we discard them in the second half, so that the task of discriminating is it the same patient or not is becoming harder. And for the second option, we modify the thresholds used to set the labels of the pairs to gradually increase the adversity of the contrastive task. So what actually we do is we not only use one threshold to differentiate the difference, but two, which I will show an example to understand what is happening, is that the difference between the two theta here makes this gray area, where if the two value of the variable can be separated by this like a mask, then the label will be 0. We are here. And if the two value is in this area, like here in this white area, using the mask, the value will, the label value will be 1. And what it does when we change theta, so this one is increasing and this one is decreasing. It reduces this gray area between the two label possibilities, so that the task of discriminating between the two values becomes harder. So, for example, from epoch 1 to 10, we set 2 values for theta, and from epoch 11 to 20, we change the values. The second detail of the training is using the negative mining idea. So we are building pairs from 1,500 volumes. So the number of samples we can make is quite high. Not considering all the pair we discard, but it's still quite important. So what we do, it's before training, we fix the number of samples, so the number of pairs we'll use to do one epoch, so the number of samples to train. And we fix the positive samples to a quarter of the value of the total number of samples. And during training, at each epoch, we sample randomly the negative pairs from the pool of all the possible negative pairs, so that at each epoch, the negative examples are different. And lastly, in the method part, what are we doing for handling the missing data? So I guess most of you are familiar with the scale.product attention, which is done in this way in the transformer architecture. What we do is that we build a mass tensor, which for each exam, t is equal to -infinity if the exam is not available, 0 else. And then we contrast this. We build this mask using MK to mask the attention and to cancel the attentions to the missing exams during training and during inference, so that we don't need to fill the missing data, as it will be given no attention in the predicting network. So first, to present the results, we interested ourselves to visualize the features we obtain from our pre-trainings. So using PCA decomposition and their association with this serum creatinine value. So each point is an MRI at a specific exam, and the color associated is the value of the serum creatinine at the time of the exam. So A is using the Sinclair method, which is a framework to self-supervise, to use contrastive learning in a self-supervised way. B is using our proposed contrastive learning based on is it the same patient or not. C is using the other option where the variable of the clinical variable which has been used is the donor's age, and D is the GFR, which is associated to the serum creatinine. But of course, the value we use to train the network is the value at the time of the exam, at the time of the MRI. So overall, we see that the donor's age and the GFR-based pre-training seems to provide the better representation regarding this biomarker. And what is interesting is that if you see this axis, can be seen as a supervision axis to the less supervised to the more supervised, and we see that the results are better having a supervision which is more important. So now for the kidney function forecasting results, so which is a classification problem, we compared two different methods. The first one is a bit custom. It's using the value of serum creatinine between each exams and extracting features which are like simple statistics on the values between each exams. The second one is radiomics, which is like in medical imaging, you use the segmentation mask to extract predefined features on the organ itself, which are shape, texture, intensities related. Then we use the pre-trained weight of some popular computer vision datasets, which are ImageNet and Kinetics on videos, because our MRIs are 3D. So for ImageNet, we duplicated the weight from 2D to 3D, and we wanted to try a 3D vision dataset, and we use Kinetics. And Sinclair is, as I said, another method to pre-train based on contrastive learning. And the proposed variable X is the method we use with different variables. So let's remember that the results are for a test set of 20 patients. So for a classification problem, like one difference in one sample of predictions make quite high differences in score. So 1, 2, 3 points is something that it's hard to like saying it's better or not. But when having bigger differences, it's where it's interpretable in a way. So first, what we can see is that in a method where we use, in a sense, like the temporal series information to try to predict the future values, we have already quite like a baseline of what we could do from this biomarker itself. And then, so yes, we forgot to say, we also compare to an LSTM architecture, and and what we do to fill the missing data is that you have different strategy, like put zeros, take the mean, or take the nearest exams. Here we use the nearest exams available, which makes the most sense for us. In the paper, we like didn't we try to see if, what was the best strategy to fill the missing data, and compared to the transformer where you use this ski mask as input. So here for the radiomics results, we see that it starts to increase a bit on the ROC, the results, using the imaging features only, which is already something we are happy, because what we want to show is that from the medical images, we have information to do this sort of prediction. And we see also that using the transformer setup enable to boost a bit the results. So yes, I will pass on those results. Like what we see is that I didn't put the results with other trainings variable donors age, for example, but they are quite equivalent to the other. And we see that like the one which use the features where we incorporated the information which is highly related to the one we want to predict after, and able to have the best results. So to conclude, we propose an approach for the challenging task of serum creatinine prediction or kidney function forecasting 2 years post-transplantation, using significant contrastive learning schemes for the DC-MRI representations, transformer architecture to input the sequential features per follow-up, and the tailored methods to handle the missing data in the follow-up dimension. So now I have like 2 slides to present a bit what I'm currently doing or future work. What I try to do is to like working on survival analysis using the imaging features, like to show that, for example, what usually doctors do is survival analysis using some clinical variables, as I said, for example, saying, okay, the age of the donor has a high potential of predicting this event or not. And what we are doing is like to try to do the same thing from our imaging features to show that in the images there are relevant information to predict the loss of the graft, for example. And what is interesting is that we have other MRI modalities, sequences, which are T2, diffusion weighted or bold. So it would be interesting to see what are the different capacity of prediction from the different modalities. And also I'm continuing trying to investigate other representation learning like ideas to incorporate medical information to the training, or to use the longitudinal information of the follow-ups. And the second thing, which is why I'm here in Montreal, is working on the ultrasound data of my dataset, which is overall the same thing as the MRI data, the same patients, the 4 follow-up exams, and several injections, because it's ultrasound data when you inject a contrast agent to the patient to better see the organ. And so it's contrast enhanced ultrasound, and we have about more than 1,000 acquisitions. And the ideas are trying to see if what we are currently doing, for example, can work with ultrasound, and to tailor the method to the ultrasound data itself, which is different from MRIs, which are videos, so to better handle the temporal dimension, or to investigate like multimodal models using both, to compare, or using both MRIs and ultrasound. So I had like examples of videos, but this is a PDF version. So what you see in dark is the organ, and at some point you see some bubbles, which are the contrast agent flowing into the organ. So yes, not really relevant here. So yes, my current internship with at Polytechnic is supported by the Data AI Institute in Europe, France. And if you have questions, do not hesitate.
Okay, Thank you, Leo. So, so do you have questions?
So, sorry. You mentioned the use of a self-supervised method. In your tables, was it CentraleSupelec? In the beginning, you mentioned that you used like some self-supervision on the patients.
So we compared to CentraleSupelec, and the patient, like what I presented using like to discriminate is it the same patient or not. I use the loss of the cosine embedding loss I've shown, so which is a bit different from CentraleSupelec.
Yeah. So because I was wondering why, if you are using this the patient information to discriminate,
yes,
why didn't you use a simple cross-entropy?
Because the goal is to like like trying to predict, for example, if I take all my MRIs and seeing the like trying to predict the variable itself, like is it what is the age of the donor? It doesn't work like in a supervised way. We're using a cross-entropy, like you said, for example.
Because we have work in the past that, it shows that for metric learning, which is basically what it is, like trying to see if it's the same patient or not, or at least learning with that, like using regular supervised loss when you have a class formation, because sometimes you don't, but you do, like it works almost better all the time. Like works better almost all the time.
Okay. Well, at first I've tried like this supervised setup and it wasn't working.
Okay.
I think I have an answer for it.
What?
Because they are low data. We showed you very high.
I don't know. Like there was a good amount of data here. Like,
it's 80 subjects or something.
Yes, the thing is the amount of volumes is quite high, but the diversity between the patients is low, and that's like most of the classification tasks we want to do are at the patient level. So trying to get information when you are, even if you have temporal information, I think there are still less diversity in the data than having 1,000 patients.
Jerome was mentioning the metric learning paper.
Yes.
My feeling is because it's low data regime. So.
But you were training a ResNet 18 with that, right? So it was on images. The volumes.
No, I said ResNet 18, but a 3D ResNet 18. So, yes.
Okay, so it was on the volume.
Yes.
Other questions?
Sorry, I didn't really get what GFR was.
So it's actually you take the serum creatinine value, and you have a formula using I think 8 weights and gender of a race of the patient, and it gives another value, which is for medical doctors more useful than serum creatinine. But the thing is, I don't have all the information to calculate it for all the points I have for the serum creatinine. But for the GFR, I have it, for example, at the time of the exam, because at the time of the exam, the doctors computed it. And it's supposed to be more, it's not supposed, it's clearly more like relevant to the graft function. And yes.
More questions? Yes?
Sure. Thanks for the presentation. I'm just wondering, so you said often that you have few samples, few patients, and I just want to understand, like, so you're saying there's a lot of variability among patients?
Yes.
But you characterize that variability in your results? So if you present like a table with results, I'm just wondering, like, what is the spread in results, or Like, do you measure something like standard error
yes.
or something like that to assess?
Yes. And
Because in practice, I think somebody would want to know if a technique is very unstable from one sample to the next versus another.
yes, and I think it's come from also that the overall like thing we want to get in the images is not, for example, one thing like if you take radiology, it's not about like seeing, okay, there is a fracture here. It's there are different information in the images, and that's why few patients, I think, is few diversities. And yes, I think we didn't do enough like statistical analysis on the results, and it would be interesting, but what we are trying to do is also trying to get more like data to validate what we are doing in external data, for example, coming from another hospital and things like that.
Yeah. But also, if no one else has a question, then I could go. So,
I do, but yeah, go ahead.
I don't know your data. I don't know your data, and I'm not, really in medical imaging. But like, are there any errors in annotation? Because I look at the images; they're very complex.
Yes.
So your ground truth is basically a segmentation map, right?
No, we don't use segmentation. We use like the segmentation is used only to compute predefined features.
Okay.
But what we are trying to do here is to, well, we extract like a region of interest around the organ to reduce the dimensionality of the 3D volume. And but we input it like as it is, like a bounding box around the organ to the model. And so, and the annotations are like diagnosis related. Like, is this patient having like
Okay.
rejection, or I simplify, but it's
Like binary.
annotations are more are more at the like classification level.
Okay. And are there any annotation errors or?
I would say no for this. Like the thing is, what is difficult, for example, is that we can have, for example, this patient at that time had acute rejection, which is an event which is in time quite. It doesn't last a long time. So maybe during all the follow-ups we have, in a sense, we cannot see it in the images. And that it's maybe where we can have errors in annotation.
Thanks.
I have a few questions. Are there other questions?
I think there is some questions.
Some questions in the Zoom, yeah.
Sorry.
In the chat.
No. If there is any.
There is Christian
okay, yes,
raising
sorry.
hands. Yeah, please go ahead.
Yes, I thank you for the great talk, by the way. So my question is, I was wondering why you did the contrastive pre-training using a CNN like a ResNet, and then passing on the features to a transformer instead of like doing everything in the transformer.
So first, the thing is, at first it would be very easy, like computationally easy, to do it in a like end-to-end way, because we have 3D volumes that we want to consider like 4 at a time, because we have 4 follow-ups. So that's the main problem, and we would need like to work with very low batch sizes, for example. And the second one is that at some point, not in this exactly setup, but at some point I've tried like a more end-to-end training, and it was like not working, like not training at all. So that's why the idea was to first pre-train the feature extractor using like all the data, all the points independently, and then to use this to feed another network.
I see. Well, thanks.
Thank you.
Questions there?
No, I don't think so.
Okay. So my comments are in regard to theta. I guess this is crucial. It's a hyperparameter, right?
Yes.
So you guys choose it and it
Yes.
change over from one epoch to another?
It's like, no, it's like every, it's every, like I did every 20 epochs. So it's like a big change and not so many changes. Because yes, it would be, like it would be very interesting to optimize this, but it would be very heavy to do it. So
basically you have an interval of difference that is allowed where you give label 1,
yes,
some kind of box function,
yes,
and then 0 beyond, and that interval change from
yes,
20 epoch to 20 epoch. So these are actually hyperparameters. So you choose them on validation, or you basically choose them from medical doctors who tell you this is a reasonable interval?
yes. First to know what would be reasonable, like what is difficult, what is easy. I ask doctors. At some point, I tried to, like, it was like a bit tested on validation,
Okay.
but not so much because it's very heavy to do it for every variable. So, like, it means I have to do several trainings for every variables. I have several variables. I have other hyperparameters to like set up, which are, I think, less important in the training than this one.
Okay, I see. My other comment is technical. So you have a function that is a box like this, which means basically between two values that are very close at the borders, you go radical from 1
Yes.
to 0. Which is, I think, it's a bit, it's not fully reasonable. So one way to deal with this is to have some kind of continuous function.
Yes.
So where you basically you get, for example, you could have a function that is monotonically decreasing of the differences between the clinical variables. And I think you didn't try something like this.
No.
Right? Yeah.
Yes.
You could literally define your loss functions like this directly, so that it will weight automatically the contrastive loss. It will go close to 1
Yes.
when the difference is small, and it will go to close to 0. But it goes smoothly. It's not radical. It's not a box function.
Yes.
You may want to try to do this and in this way you will have just one hyperparameter. In fact.
Yes.
Just
And
one hyperparameter.
maybe it could be even be like learned, for example, like
Perhaps
in the contrastive, like in the contrastive loss, you have this temperature parameter that in the first paper, I think it was set as hyperparameters, but in some more recent papers, they put it as learnable parameters, a learnable parameter, which is like one less hyperparameter to tune. But yes, I don't know exactly how I would do it, but maybe, yes, it's interesting to mention.
so. There's something called Laplacian graph Laplacian regularizations, which is related to this, where people basically, if you know that two data points should be close to each other according to some clinical information, for instance, then you create some continuous function, pairwise functions, that pairwise potentials that tell you this is close or not, and it's a continuous function, it's not a box. And then you multiply this by a term, which is basically will be the difference between the embedding. So it will tell you, you will pay a high penalty if that function of similarity is small, it's big, sorry, then you will pay high penalty if you give them different embedding.
Yes.
This is very common in graph learning and things like this. So I think it might be useful, better than a box hard box function, I think. Other questions?
Can I ask a quick question about the survival analysis?
Yes.
Do you adapt the same models that you use in classification to do survival analysis? You change the cost function, or you use some kinds of specific models for survival?
For the moment, I've used like classical Cox models
Cox.
from the imaging features. Like I take my encoder, I generate the features, and I use like the classical Cox model to fit and see if I can get a good prediction score from the imaging features.
So the last layer is a Cox model.
Yes, yes, and you freeze the encoder. So that's why I say I generate the features, because I don't fine tune the encoder along with the Cox model.
Yes. So the output will be the probability of the hazard at each follow-up session.
No, and I use, like, for example, one exam at a time. Like all the exams at the first, I see like from the first exam I have those results. For the moment, I do this like separately.
So survival analysis, this is related to oncology or the same problem after rejection?
No, it's like when you have it's sort of a classification problem when you have like events which can happen in a period of time, and what we have is like from the transplantation date, we know everything is okay, and at some point maybe this patient have a rejection, chronic rejection,
Okay.
and this is the event we consider.
Okay. Questions? I guess everybody's hungry. Well, let's thank you.